Hello everyone, my name is Wei Bao. I'm from School of Information Technologies of the University of Sydney. So today I'm going to present my work. So it's about this user mobility analysis in this cooperative wireless networks. And this work is authored with my colleagues, Professor Li and Professor Washington. So at the beginning, I need to give you some brief introduction. So in traditional mobile networks, users are associated with a single base station. So that means a user is served by one base station. But this is not very ideal because, like, if the user is very far away from nearby base stations, then the performance of this user is very bad. So in order to address this issue, so we have this base station cooperation. So that means the user can be jointly served by a set of multiple base stations. So in this case, the probability that the user is far away from all of these base stations is smaller, right? So in this case, it's like not that likely that the user enters this test mode. So that's why we need this base station cooperation. So this could be a very important feature in next generation mobile. So in this base station cooperation, we have these two clustering modes. One is called this user-centric clustering, and the other is the disjoint clustering. For user-centric clustering, so each user is served by this individually selected cluster base stations. So that means, like, I can select this cluster of base station and you select another set. But in this one, we consider this disjoint clustering. So that means the network is statically partitioned into non-overlapping clusters, and the clusters do not change. So in this case, and we consider this one because it's easy to implement. So we don't need to consider this very complicated, like, user scheduling and this resource allocation problem. So in this paper, in our work, we consider to characterize handoff in this disjoint cluster base station operation. So this is more complicated compared with the single base station association. So this is because, like, in single base station association mode, like, handoff involves this change of base station, just like single base station. So I change from like this base station to that base station. Only two base stations are involved. But now, because we have like the clusters of base stations, so in this case, if there is a handoff, so like we change the set of multiple base stations. So in that case, we need to characterize this cluster boundary instead of like the cell boundary. So here, this cluster is the region that a user connects to the same set of base stations. So if like I'm covered by this set of like base stations, okay, so I'm in this cluster. And if like I cross this cluster boundary, okay, I make this handoff. So in that case, and the handoff corresponds to the crossing of cluster boundary. So let's see some examples. Okay. So in this example, okay, so we have like a single base station association. So here we can see, okay, so this small circle corresponds to this base station. And in this scenario, okay, so we have this blue lines corresponding to this cell boundary. So say like if I'm here, okay, so I'm going to connect to this base station. If I'm here, I'm going to connect to this base station. So if I'm moving from here to here, so I'm like crossing this cell boundary, then I'm going to make a handoff. So in this case, we can see this the handoff corresponds to this crossings of the cell boundary. Then let's look at what happens if we have like a cluster operation. So in this case, we have like 4 clusters. So if the base station is in this square, okay, so this square, okay, so it's cluster 1. If the base stations are in this square, is cluster 2. So in this case, okay, so we have these clusters of base stations. However, we can see that this cluster boundary is very complicated. This corresponding to this black line. So why? So this is because say like if I'm here, so if I'm here at this place, I'm going to connect to this coldest base station, and then I'm going to reserve all these base stations in the same class. So by doing so, okay, so we can see that this black lines correspond to this cluster boundary. So this cluster boundary is quite different from just this square. So the shape is quite different. So we can see this handoff corresponds to this crossing of this cluster boundary. So if like I'm moving from here to here, okay, so I'm crossing this cluster boundary and then I make a handoff at this in this situation. So in this work, we are motivated to study something very interesting. We want to study this, okay, which is the average number of cooperation base stations set. We want to optimize this K. So what is the best cluster size? So this is debatable in terms of many factors, but in this work we consider the optimal trade-off between the data rate and this handoff cost. So larger K will lead to this higher handoff cost, but also higher data rate. Smaller K means like lower handoff cost and lower handoff cost. So we want to find the optimal K to balance this handoff cost and data rate. Okay, so in order to do so, and we need to characterize the handoffs under different K. And we also need to find this data rate and approximated data rate under different K. And then we find the optimal. So we consider the system with like one tier of base stations, and the base stations form this Poisson quantity with intensity of lambda. Okay, and we also have this square grid with edge length A. So base stations in one square belong to the same cluster, as I just shown in the previous figures. So the K is equal to lambda times A squared. And we use like T1 to denote the set of cell boundary, and the T01 to denote the set of cluster boundary. And as I just showed here, so this blue lines correspond to T1, okay? And this black lines correspond to this T01. Okay? So this T01 is subset of T1. Okay. Then next we need to categorize the handoffs. Okay. So in order to do so, okay, the first step is we need to categorize this line intensity of this T01, the line intensity of the blue lines. Okay. So what is this line intensity? Is defined as the expected length of T01 in this unit square. Okay. So it's formally defined here. So the expected length of T01 is unit square, and this term means one-dimensional back measure. It's just a measure of this length. So this is T01, so that's mu1 of T01 means the average total length of this boundaries in this unit square. However, these lines are very difficult to calculate directly. So in order to do so, we need to consider this delta T neighborhood. So we study this delta T neighborhood of T01, which is denoted by T02 delta T. Okay, so this delta T neighborhood, like a point is in the delta T neighborhood if and only if the distance between this point and this line is smaller than delta. And then we can categorize, we need to categorize this average intensity of this delta T neighborhood. So this average intensity is defined as this expected area of this delta T neighborhood in this unit square. And this term corresponds to this two-dimensional back measure. This is the measure of area. So let's see this example. Okay. So suppose like we have this circle. Okay. Then its delta D neighborhood is just like this red region. And then like suppose like we have a line segment, okay? And then this delta D neighborhood is just like this red region. So why do we need to characterize this delta D neighborhood? So because like we have this length of the curve is equal to like the area of this delta D neighborhood divided by 2 times of delta D. And we let this delta D approach to 0. So by doing so, we can characterize the length, like by characterizing the area. And let's return to the problem itself. And then like we want to characterize this area, okay? And then we convert this area to the probability. So that means, okay, so the area intensity is equal to the probability that a uniformly randomly selected point falls within the delta D neighborhood. Okay? So basically we have like this mu2 is equal to the probability that a randomly selected point falls within the delta D neighborhood. Okay? So let's go back here. Say, okay, so if we want to characterize like this area, okay, we can just randomly throw some points on the plane. And this area is just equivalent to the like, probability that this point falls within the area. So by doing so, okay, we convert this area to this probability. And actually in this original problem, okay, so we can characterize these probabilities by this stochastic geometric approach. Okay, so because like we consider the Poisson point process, and then we use some like assumptions and like conclusions based on this PPP, and we can get some probabilities, and we can get the probability that the random point is within this delta D. So finally, by taking this delta D approaching to 0, okay, and then we can characterize this line. As I just introduced, okay, we divide the area intensity by 2 times delta D and get this line. So finally, we get this line intensity, okay, and we rewrite it as a new A lambda because this is a function of like lambda and A. But this is not in closed form. But we have some good things. Okay, the first one is the scaling property. Okay, so we multiply this A by capital A times and divide this lambda by capital A squared times, and we multiply everything by capital A, and they are the same. Another good thing is that, okay, so if like this lambda A squared is much greater than 1, then we can get this asymptotical expression, which is in closed form. Okay, so this is in closed form. This is pretty good because like the lambda A squared means the K, the average number of base stations per square to cluster. So this is pretty common. In this case, if like much more than 1 base station in 1 cluster, we can use this equation. And finally, okay, we can directly get this handoff rate, which is defined as this average number of handoffs per unit time, just 2/5 times the line intensity times the velocity. This is not difficult to understand because like if the boundary is more dense, right? So we have more handoffs. And if the user's speed is like faster, then we have more handoffs. So this is just proportional to the line intensity. Okay, and then we also need to characterize the data rate under K to find the optimum. So here we consider this Downlink data rate, and we consider this non-coherent noise transmission tool. We consider this interference limited model so that the noise is wrong. In this case, like everyone in the same, every base station in the same cluster will generate signals, and everyone not in the same cluster will generate interference. So this signal to interference ratio is just like the sum signal over this sum interference. Okay, so this phi in means the cooperative base station in the same cluster. And this phi out means it's non-cooperative base station. And this H term corresponds to this like fast fading term. We just assume that they are exponentially distributed. And this one, okay, so can be easily derived by this stochastic geometry analysis. So we can derive this average user data rate. However, this is still not in closed form, but with multiple levels of integrations. So we don't want to directly use them because like those like expressions with multiple levels of integration do not give us like much like, insight. But the good thing is that we still have this scaling property. Okay? So if we multiply A by capital A times, and we divide the lambda by capital A squared times, and they are equivalent. So in that case, we can see only K, which is equal to lambda A squared, matters. So in this case, actually, we can see this data rate just like a single dimensional function. So we can characterize this RK in this offline fashion. And then we can also use like this curve fitting to approximate this data rate. Okay, so like we use like this one for this RK, so to approximate this data rate, and we found that this the unit of fit is pretty high, and this D is zero in the range of 0.5 to 0.5, and this beta is in the range of 5 to 6.5. So that depends on this path loss volume. Okay, and then finally we want to like find this the overall utility of the user, which is just a weighted sum of this data rate and this handoff. Okay, so this W1 is the penalty weight for this handoff, and the W2 is the gain weight for this data rate. And also here we need to multiply by 2K, because like 2K is just the number of base stations involved in one handoff event. Say like if there are like more base stations involved in one handoff, and there are more higher penalties. So in this case, we also need to multiply this penalty term by 2K. So then we can use like for this term, okay, so we use this asymptotical equation derived at the beginning, and this one we use this fitted curve, just so this one with this one. So in the end, of this utility, overall utility is in closed form, and we want to maximize this overall utility. Then like we can directly get this optimal, okay? So in this equation. So here we can see that this, like if we increase like user speed and we increase the density of the stations, right, and the optimal K will be. So I think that this equation gives like very important insights, like how can we design this optimal cluster size. Okay, so finally we use like this simulation to evaluate our applications. So first, let's see like the user utility under different values, okay, and under different lambda values. And this vertical lines correspond to this K, optimal K, and this. So this corresponds to this optimal K by simulation, and this dotted lines correspond to this K star derived by our approximative formula. Okay, so we can see that this K optimal K is pretty close to this star, showing that like our formula that in closed form is useful. And also we want to show this optimal cluster size K under different lambda V values. So basically here we can see so by simulations and by this our expression. So in this case we can see that the simulation results and this our analytical results are very close to each other. And also we show that if we increase the value of lambda and if we increase the value of user speed, actually the optimal cluster size. Okay, so finally I need to make a brief summary. Okay. So in this work we consider this a disjoint cluster base station configuration, Okay, so we want to find this optimal cluster size K by balancing this handoff and this data rate. For this handoff, we use this stochastic geometric analysis to characterize like the line intensity of the cluster boundary, and then we can characterize this handoff rate. For this data rate, we consider this non-coherent joint transmission, and we characterize the data rate, and then we use this repeating to get this closed form, this data rate. And finally, we get this optimal K in closed form, and then we use like simulation to validate. Okay, so that's all for my lecture. I'm very happy to